let's drop into the Tools folder and you'll find a file called linker.py. Now before we go through this file and describe exactly what it's doing, let's actually use it and then we can understand what the linking process actually does for us. Now we have 6 separate library files and we have to assemble each of those. So we will have machine code for each of those files. We have to join the machine code together into a single file. And this machine code file becomes our operating system. And then we can load this up into the ROM. But of course, if we were to generate 6 individual files, and we've got lots of subroutines for each of those files, we have to be careful and make sure that there isn't any overlap in terms of the positions within the memory within each of those files. So you can see at the top of this file here, we've got the command that we can use in order to link the files together. But we don't need to use this command. We've got an automated system already set up. So if we head into this file here, it's called Make.os. It stands for Make Operating System, and this is a command that we can use within our Visual Studio Code Editor. So if we click on this, you can see that what this does is it opens up each of the library files. It then assembles the library files, and at the end it goes through and it uses that command which we just seen a second ago in order to link each of the machine code files which we have just generated for each of the libraries. And then finally it will make a final file called OS, which is our operating system. So how do we run this make OS command? Well, the same as we run the other commands that we have. We go to Terminal, Run Task, and we have one here that says Make Operating System. So in effect, this Make Operating System, whenever we click it, it will run this Make OS command. So we'll do that now. And we'll have a look at the comments at the bottom. So you can see here, it's going through and it's assembling the BIOS and the maths lib, graphics lib, string lib, fixed point, floating point. So that's it going through the assembly process in order to generate the machine code for each of those library files. And then we're going through the linking process. So the linker has to take all of these individual machine code files and assemble one operating system file, which is called os.mc. So let's head in and we'll look at the operating system.mc file. So if you head into the MC folder and head down to os.mc, then we've got this file here. Now this is what we're going to load into the computer's ROM, and in effect it acts as our operating system. So it's going to start off, and we've seen these lines before in previous courses. It sets up the stack pointer. Now what we have here is all of the subroutines within all of our libraries, but of course they're in machine code now and they're beginning at particular addresses. Okay, so if we head down, we can see we've still got a lot of space available. And you can see individual routines here. And there's a few lines of space left between each of them. So these are all of our library function subroutines that we've got access to within the ROM. Now, just to be clear, whenever we start our machine, at first it's going to go to the very first position within the ROM. Now, the first couple of commands here are used to set up the stack pointer. The next couple of commands here are used to jump to the location 8000. Now, the location 8000 is the beginning of the RAM. So that then starts running through the actual program. And the program will run, and then within the program it will jump over to subroutines within the ROM, and then within the ROM it will return back to the original program in the RAM. So that's the basic structure of how our code runs. So if we were to add an extra subroutine to one of our library files, so for example, if we went into ASM and we went into, say, the floating point library, if I was to come to the bottom of this here and I was to decide that I wanted to add in some other routine, then I could add in a subroutine here, and then I could save the file. But of course this isn't going to do anything because it's not been loaded into our machine. So at that point, once I've changed this file and I've saved it, I can go to Terminal, Run Task, and I can click on the Make Operating System. And it will go through the process of generating that MC file. And then we can take the MC file and we can load it into our machine. So we can drop into the computer, and we're interested in updating the ROM. So we right click, Edit Contents, and you can see we've got the existing values for the ROM which have already been uploaded. So we can open, and we're in the machine code folder, and we head up to OS. So there is os.mc, open up, and it will load in the updated operating system. Now what we want to do is we want to be clear exactly how we use all of the memory within our ROM, and we want to be clear about how we use the memory within our RAM. So what we want to do is re-look at the memory map. Now we've looked at a memory map before, I believe in Design a CPU 2. So we'll need to go ahead now after making all of the changes and look at a new memory map, and we can do that on the next video. So just to be clear about the interaction between the RAM and the ROM, the RAM contains the program that we are actually running. It's random access memory. So whenever we close down our CPU, all information within the RAM disappears. It all just goes back to zero. But the information within the ROM remains there. Even if we close down the simulation and open it back up, all this information remains as it is. So what we would do is we would generate a piece of code in the assembly language, and then we would assemble it into machine code. We take that machine code and we load it into the RAM. Now that machine code is going to have some jumps to subroutines. So it's going to run through a few lines of code within the RAM, and then it's going to say, in order to do the next part of the program, you're going to have to jump to the ROM. And within the ROM, you're going to have to go to a certain address, and that address is going to contain a subroutine. So it might come down to, say, for example, this address here, and it will run through the subroutine. So in effect, run through the program now from here inside the ROM, and at the very end, it will return back up to the calling function. So it will return back up to the next position within the code within the RAM. Now, another thing that obviously might happen is that we could have a subroutine. It could call a subroutine from the RAM, so it goes to the ROM, and then it could get to, say, this point here, and within this subroutine there might be a call to another subroutine. So let's say it gets part of the way through, say to this point here, and it might call another subroutine. So it doesn't jump back to the RAM, it jumps back to another position here within our ROM. Let's say it jumps to this position, and then it starts writing this code. Now this code here in turn could call another subroutine. So in effect this would be a triple nested subroutine function. So it would call another function here, and it would run through this function, and then at the end of this function it would return back to this position, and this function here, or subroutine, would return it back to a position here, and this one would return it back to the original position. It would finish off the code, and then it would jump back to the correct position within the RAM. So that's what's happening all the time whenever we are actually running our code. We're jumping about between the RAM and the ROM, and when we're in the ROM, we could be going through multiple nested subroutines in order for the full program to run. So the great thing about this is that it means that the assembly language code that we have here within the RAM can be quite small, and the function that it actually generates could be quite a large function or quite a large piece of code, but all of the code is held here within the ROM, and we don't need to continually write new code or continually write the same code over and over again. Now let's have a look at the linker code that joins all of the machine code for each of the library files together and creates the operating system machine code, which we then go ahead and load into the ROM. So we have our linker here, and as we said, the main function of this code here is to read the individual machine code files and then to join them. But it also checks to see whether any of the addresses within one machine code file for one library is in conflict with any of the addresses for the rest of the machine code library files. So the last thing we want to do is have us writing one library file over the top of another library file. And that's the main point of the code, and that's what this code does for us. And then finally it outputs the file as os.mc. Now one thing to note that we have to be careful about, if we head into the ASM and we pick out, for example, the floating point library, then if we were to note that within this library we've got a subroutine, which is just a function. But within this function, we might actually have local variables that we're using within this function. So those local variables will actually exist not in this ROM, but they will be generated in the RAM. So if we come down to the bottom of the file here, you'll see that we've got a .ram, and this .ram data for this particular library file is starting at 0x C180. So all of these define storage directives are used locally within the subroutines within the library, but they actually refer to a RAM location. So they're just temporary, but they're only going to get used when particular subroutines are called. So we're going to have to be careful that these values here for the .ram don't conflict with the values for the .ram for the other library files. So for instance, if we were to open up the fixed point library file and head to the bottom, you can see we've got the .ram files, .ram locations for this particular library. So we'd have to ensure that there isn't any overlap between these as well, and that's also something that happens within our linker. Now, one other thing we have to be careful of when we update the library files is that we do give unique addresses for the individual subroutines. So we want to make sure that all of these are actually unique and they don't overwrite each other. Now that's easily enough done. What you can do is you can head into the actual ROM itself. So if we head in here and we can have a look, and let's say we are looking to extend on, for example, the BIOS library. So the BIOS library sits near the beginning, so the BIOS library is round about here. So this will be the BIOS library here. If we wanted to add another routine to the BIOS library, we could just pick, we could leave this line blank and we could pick, for example, location 0x0210, and we could start the code from this particular point. So it means that whenever we generated a new string, a new BIOS function, this would be our address. And that address would be added in here, okay? So it would be EQU, and then we would add in the new address. But of course it wouldn't be in the fixed point library, that would be in the BIOS library file. So it's relatively easy to find the position that you require to add in any new code or any new subroutine to a library. So there's quite a lot of detail in this video. Take your time to review it, and as we work through the rest of the course, we will be going in and out of these libraries quite regularly. So you'll get used to the actual format and what they look like and exactly how they work. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.